AP Chemistry, folks. We're going to go through some of these net ionics today. This is learning objective 2, and we're just going to be working on mostly those net ionics here, right here. I've done predicting products in another presentation, so you can find information about that. And there's also another presentation on how to do net ionics. So I'm not going to go through every single different option. You can go to that for extra help. I just want to show you some of the answers here so you can double check your work. Let's see. Let's go ahead and try that very first one that's listed. We have silver nitrate and sodium sulfate. We have a double replacement reaction here. We end up with silver sulfate and sodium nitrate. And so we can balance this guy. We have the silver, two silvers, nitrates. We're going to have to put 2 there. Should be good. Now we can go through and identify the precipitate. Sulfates are usually soluble here unless they're with silver. If they're with silver, it is going to be our precipitate. So there's the precipitate. Let's go ahead and break this thing up. We have 2 silvers, 2 nitrates, plus 2 sodiums, plus sulfate gets us to 2 silver, 2 silver sulfate, which is a solid, plus 2 sodiums, and 2 nitrates. We can start canceling things out. They cancel. We'll cancel them out with red here. The nitrates are going to cancel, the sodiums will cancel. We're left within those things in our net ionic, so we can rewrite that. 2 silvers plus sulfate makes AgSO4, which is our solid. And we need a 2 there. And here's what I'm missing, a 2 there, and 2 there. Now I get rid of this. Sorry about that, the whole balancing thing. I didn't transfer that subscript 2, and that kind of threw things off. Let me get rid of this here. Now we're good. All right, let's go through and try another one down here. Let's try A down here. All right, sodium sulfide and zinc chloride. We're going to end up with sodium chloride and zinc sulfide. We can balance this thing just like that. Go through and identify our solid. It's going to be the zinc sulfide. 2 sodiums, sulfide with a -2 charge, zinc, the +2 charge, plus 2 chlorines, negative. Now the product side, 2 sodium, 2 chlorine, ZnS, which is a solid, so that's going to stay together. Now we can go through and start canceling out the spectators. That sodium's going to go, that chlorine's going to go. We're going to be left with our sulfur, our zinc sulfide. And we have it done. Okay. See which the next one we can try. All right, number 23 starts us off. So let's try this one. That one looks like it's going to be a fun one. All right, we have our sodium nitrate and copper sulfate. Those are our reactants. NaNO3. NaNO3 plus CuSO4 gets us Na2SO4 and CuNO3. The copper 2 nitrate is still a positive, or the copper here is a positive 2, just like it is over here. And so we end up with 2 nitrates over here on the product side. Now this one's neat or interesting because we have something that's soluble here. This is going to be aqueous. Aqueous. This one's going to be aqueous. Alkali metals are always soluble. Nitrates are always soluble. Sulfates are usually soluble. It is with copper. We have over here, sodium is an alkali metal. That's going to be soluble. We have nitrates over here, which is soluble too. So everything here is going to be soluble, which means that this is going to be no reaction. Nothing here to do. A reaction doesn't happen. They just kind of sit there and stare at each other. All right, let's go down to some acids and bases. This first one here, I guess I'll do all three of these. I'm going to do the first one and then letter C and then come back to B. The first one here is something that we haven't talked about yet, and I guess I wouldn't really expect you to do this on a quiz or a test at this point, but it is something we're going to be looking at later on in the year, so we can go ahead and look for it. So when we have this weak base, this ammonia, reacting with an acid, like hydrobromic acid, this is a strong acid, we end up with NH4Br, ammonium bromide. And I'm not going to work with anything more than that, just to show you that that's the product. So we'll work with this particular kind of reaction later on. But let's go ahead and skip the C down here. So here on your packet, just if you want to do that, that's fine. All right. Let's go ahead and go to C and look at that guy. We have perchloric acid here, which is a strong acid. We have magnesium hydroxide, which is a strong base. We can go through and we have an acid-base neutralization reaction. We always get water. And we always get then whatever is left, which is going to be magnesium perchlorate. We can balance, 2 here, 2 there, and we're good to go. And then we can write out our net ionic, or total ionic first. So 2 hydrogen plus 2 perchlorate, magnesium hydroxide, which is going to be a solid, 2 water plus MgClO4, 2, and that's aqueous. So kind of the weird thing about this one is that it has this solid in here. So magnesium hydroxide is actually not going to be soluble, but when it reacts with the perchloric acid, it will. It's kind of like throwing baking soda into vinegar. The baking soda starts out as a solid. It doesn't have to be a solution at the beginning. So that's what this is. And magnesium won't dissolve either. So there's that. So when we go through this, we actually don't have anything here that we can cancel out because we have our water, which is going to be our liquid, and then we have our different pieces here. So there's that. So we have a strong acid, we have this strong base, but that base is a solid. So that's what makes this one kind of special and difficult. I do want to show you a different one. Let's say instead of doing magnesium hydroxide here, we did calcium hydroxide, which is going to be soluble. So that's aqueous. So we get the exact same products, only instead of the magnesium here, we end up with the calcium, CaClO4. And there's that. And then we can balance. So it's going to be balanced the same way. 2 here, 2 there. We split everything up. 2 hydrogen, 2 perchlorate, plus calcium, plus 2 hydroxides. Makes 2 waters. Those are liquid, plus calcium, plus 2ClO4, which is minus. And so we can start canceling things out now. We can cancel out the perchlorate. We can cancel out the calcium. We're left with hydrogen, hydroxide, water. So this is the thing here. This is the case we talked about in class. Anytime that we have a strong acid and a strong base that's soluble, should have said that earlier, that's soluble, we're going to be able to write the exact same net ionic, which is the hydrogen plus the hydroxide makes the water. And we have that. All right, so let's go up to the one right above it, which was a weak acid. This is not a strong acid. So strong acids are strong electrolytes, which means they dissociate 100%. Weak acids are weak electrolytes, which means that they don't dissociate 100%. Therefore, when we write the net ionic reaction, we cannot split this thing up. This thing stays together because there's still some of that in solution. We don't have just hydrogen ions and phosphate ions. We have some of that thing bonded together as it is. So let's go ahead and work on this guy. We'll predict the products. Barium phosphate. I think I did that backwards. Oop. 3 there, 2 there. And then we have the water, H2O. Now we need to balance this thing out. I think, let's do 3 here. There's the 3 bariums. And then we're going to need a 2 there. That means we're going to need a 6 there. And we're good. So we can go through this thing. The barium hydroxide is soluble. So we have our 3 barium plus 6 hydroxides. Now this thing stays together. This does not get broken apart. So we're left with 2H3PO4. Makes this thing over here. Barium phosphate is not going to be soluble. So that's kind of one of the weird things about this problem, is that we have not only water, but we also have a solid. So there's our solid, there's our liquid. We have Ba3PO4, 2 is a solid, and 6 waters. So this one is different because this is as far as we can go. This is our net ionic reaction. There's nothing to cancel, and sometimes that happens. The total ionic is going to be the same thing as the net ionic. Let's see what we have next. Perfect. So we have another weak acid here. So let's look at this one here, because this is going to be a weak acid strong base. Here's my weak acid. Here's my strong base. So just like we said before, anytime that we have an acid-base neutralization reaction, we get water and whatever is left. And then this one becomes a little bit more straightforward than the others. It's neater, first of all. We don't have any balancing to do. All the charges are positive one, negative one, so it just works out well. This is going to be liquid here. Forget about that. Weak acids, again, do not dissociate completely, so this thing has to stay together. This one does split up. Water stays together. And this guy, potassium acetate, splits up because of that alkali metal. So we can cancel out the stuff we can cancel, which turns out to be that potassium. That's it. We're left with CH3COH plus hydroxide, water, and CH3COO. This is going to be a liquid. Get the negative charge in there, and we're good. So this kind of weak acid strong base equation is really important for chapter 15 work, much later on. But just to introduce you, this kind of stuff doesn't go away. We still use it throughout a good chunk of the year. All right, let's go through and see what else we can find. These are the oxidation ones you guys moved. All right, so we have some Single replacement reactions, these are going to be acid metal reactions, this one here. So we have single replacement where the copper and the hydrogen switch places. So we're left with hydrogen gas and CuCl2. We're going to say copper in this case is positive 2. And that's a usual oxidation state of copper, so we'll just probably say positive 2 from now on if it doesn't list, and so we can come up with the correct stuff. So this is going to be aqueous on this side, and we can split things up. This is a strong acid, so copper solid plus hydrogen, color balance, 2 hydrogens plus 2 chlorines makes hydrogen gas, copper, and 2 chlorines. Now the only thing here that we can cancel is going to be those chlorines. The copper we can't cancel because we have a solid here, we have aqueous here. Solid, aqueous. That means that they can't be canceled. They have to be in the same phase. So we can go through and write the final one. Copper solid plus 2 hydrogens gets us hydrogen gas and our copper ions. The next one here is going to be halogen replacement. So we're going to take this halogen and replace it with that one. So we'll end up with sodium iodide and bromine. That turns out to be a diatomic as well, and that is a liquid. Now remember that we go to the activity series to figure out if these things react. So we go to the activity series of metals for this one. And again, that's something you can just look up. And in this case, copper will react with hydrochloric acid in order to form that hydrogen gas. So we went through that one, and you wouldn't be expected to memorize that, but we should have looked it up and shown that was the case for this one. For this one down here, though, we do memorize that activity series of halogens. It's F, Cl, bromine, and iodine. And now iodine is lower on the activity series than bromine is, and so this does not happen. All right, let's erase all this. Any others here that look like something we should look at? These are all precipitation ones and acid ones. Some more here. Those are metal, acid. Let's do this one here. We didn't do an acid carbonate as an example, so let's look at that one. Here is calcium carbonate. Let's see if I can get some room here. CaCO3. So this is some practicing with your right out chemical formulas. Calcium is positive 2, carbonate is negative 2, and then we have our acid H2SO4. That gets us water and calcium sulfate. And water is going to be a liquid here, and calcium sulfate, this is again one of those frustrating ones. Anytime we see sulfates, I get a little nervous because I'm not sure exactly if I remember my solubility rules for sulfates, but they're usually soluble. They're not soluble when they're with lead, calcium, barium, or strontium. Also silver and mercury, those in there as well. But this one is going to be a solid. And we also get carbon dioxide gas. Sorry about that. So we have calcium carbonate, which is our carbonate, and we have our acid here because of the hydrogen. Anytime we have an acid plus carbonate, we get water, carbon dioxide, and whatever's left. Water is going to be a liquid. Carbon dioxide is going to be a gas. And we have whatever left in this case is going to be that calcium sulfate. We can split things up here. actually maybe we can't. Calcium carbonate in this case is going to be a solid. Carbonates are solids. This is going to be our only thing that we can split up. 2 hydrogens plus sulfate. And then we don't split up the water, we don't split up the calcium sulfate, we don't split up the carbon dioxide. So this is right here. Let's do it in blue. The net ionic reaction for that one. See if we can find a little bit of a better one where we have some soluble stuff and also doing a carbonate. I think this one here is going to give it to us, number 12. Sodium hydrogen carbonate and nitric acid. So again, we're going to block this off. Sodium hydrogen carbonate is another word for baking soda. And then we have nitric acid, which is HNO3. Strong acid, it's nice to work with. And we have our baking soda here, which is NaHCO3. It was correct up there. I'm just going to maybe try to write a little bit neater. NaHCO3. We end up within water, that carbon dioxide that I had forgotten that last time. And then whatever is left. We've always talked about how subscripts don't carry except for polyatomics, so this carbonate subscript should carry over here. This is the one case where that doesn't apply, where the carbonate gets broken up into its different pieces to make water and carbon dioxide. So keep that in mind. And now we can balance. It's balanced. Let's go ahead and separate this stuff. One of the reasons why I wanted to do this one is because of that hydrogen carbonate. Hydrogen carbonate is a polyatomic ion that stays together. So we tack that hydrogen on, it stays with it. And we have nitric acid. Water stays together. Carbon dioxide gas stays together. And this one does not stay together. Sodium and nitrate break apart. So we can start canceling things out. Sodium's going to cancel. Nitrate's going to cancel. And then we're left with our bicarbonate and hydrogen mixed water, carbon dioxide. Sorry, bicarbonate is another word for hydrogen carbonate. There we go. All right, ladies and gentlemen, that's all of these that I'm going to do for you. There's a lot of practice here. If there are some specific ones that you want to see that I didn't cover, you can go ahead and put them in the comments, and I'll get to them when I can, or I'll put the answer down there at least as I get there. Otherwise, enjoy. Keep on fighting the good fight for AP Chemistry.